Okay, we're going to continue studying reactions of alkene and alkynes and contrasting them. So let's go now for the hydrogenation. So I'm going to erase this as hydrogenation reactions that we're going to be doing now. So we're going to be adding hydrogen across the double bond or the triple bond for that matter. So let's see, I'm going to draw the metal cyclohexene again. So here, a couple of things that we need to know when we're doing predicting products. And one condition for that is hydrogen in platinum or palladium maybe. So important that this reaction is a syn addition. Important when you need to predict stereochemistry. So if we draw in the products here, you're going to be adding the two H's to the same side. Let's do another pen. What that means is, in this time, I'm going to draw the H's. So say that I have a metal here, then that H means that I added it this way. Of course, there was already an H here, right? And so these two are the ones that were added. But let's, I'm going to do a change. Let's say that instead of doing this with hydrogen, I'm using deuterium. So, and let's say that I'm using platinum. So the reaction is the same, it's a hydrogenation. Remember that deuterium, what it is a heavier, is an isotope of hydrogen. So same atomic number, but double the mass. So in that we represent with a D. So, but it will react exactly the same. It will add to the double bond, and it's a syn addition. Now let's look at the products now. What is the product? I need to be adding the D's in syn fashion. So if I put the D here, the other D needs to be to the same side. And now here you can see that it has consequences then. So pay attention to that. Syn addition means same side. So now when you're doing this, this is a chiral center. Now this is also a chiral center. When we do Canning-Gold prolog priorities, deuterium has higher priority over hydrogen. So this carbon will have 4 different substituents. Deuterium, hydrogen, this chain different to that. So that's a chiral center. And this is also a chiral center. Metal, deuterium, chain, the sun, different to that, so forth. So we will form that plus the enantiomer. So it is a syn addition. The other thing that we can have, either hydrogen or deuterium, is that we can change the catalyst and do, let's say we're either or. Here we can do, I'm going to add to that Wilkinson's catalyst. This, what it is simply the reaction when you use a metal is heterogeneous catalysis. Wilkinson's allows you to do homogeneous catalysis, which means everything in one phase. But it will produce the same outcome. It is a syn addition. Now let's do the hydrogenation of alkynes. And we're going to be doing this time an internal alkyne. So if I do, we can, in the case of hydrogenation of alkyne, we're going to see 3 different conditions. Say that I'm using the same here, hydrogen with platinum or palladium. This is going to do, and let's say we're going to be adding 2 moles, let's say, of hydrogen. So we're going to end up forming an alkane. So hydrogenation of alkynes, in this condition, will give you an alkane. Butane in this case. This will be 2-butene. So the alkyne give you an alkene. Now, we can do also hydrogenation of alkynes, partial reduction. So from the alkyne, get the alkene. And there's a couple of conditions that we need to study here, which this is what's different from alkenes. Here you just have add 1 mole of hydrogen, and that's it. You get from the alkene an alkane. Now here you can get, you can use one condition that's called using a poison catalyst. So if you use poison catalyst, what it is catalyzes the conversion from alkyne to alkene, but does not catalyze the conversion of alkene to alkane, so it stops at the alkene. Poison catalyst examples are Lindlar, and here we need to remember that name, Lindlar's catalyst. We can also have other nickel boron catalysts, so poison catalyst. Again, what that is we're going to be hydrogenating, adding 1 mole of hydrogen, you're going to form an alkene. But this reaction is a zinc addition, and from this alkyne, we're going to get the cis alkene. And because the mechanism here, this is a zinc addition. Remember that word, zinc is about the mechanism. In what fashion are you adding this? Here you're adding same side, same here, because you're adding the 2 H's like that to the same side, you're producing the cis alkene. But I'm gonna remove that, and we need to remember that. This condition is to get the cis alkene. There is another condition now that is also a partial reduction, partial hydrogenation, but to get the trans. And this, in your textbooks, and you will find the wording dissolving metal. And what it is using an alkali metal, such as sodium, in ammonia, liquid ammonia, for example. It could be another alkali metal, but this is what we're using, NH3. What it is, I'm not going to draw the mechanism right now, but I have it in another video if you want to check it out. But the idea is that goes through an intermediate. Sodium transfers 1 electron. Sodium, the atomic number is 11. So the electronic configuration of sodium is, say, a neon core, electrons, and then 3s1. So sodium is capable of oxidizing. It oxidizes easy to sodium plus 1 electron. So this reaction is a radical reaction. It produces an intermediate, the following fashion. We're going to form a radical. The intermediate is a radical anion. That's important because of the mechanism. Having that intermediate is what defines the product that you get is trans. The reason for that is that here this is avoiding, say, repulsions, electronic repulsions. So here you have already the 2 groups, the 2 metals that we have here opposite to each other. So we have proton transfer step. This we get a transfer, another electron transfer. So several steps involving electron transfer and proton transfer to get to the final product. The final product is the trans alkene. So summarizing, what's different, what's the same? We're adding hydrogen to that. But in the case of alkenes, we're adding just 1 mole of hydrogen. Remember, this is a zinc addition, same side. And I gave you the example with deuterium to show, to better show that. You can also use deuterium in alkynes, by the way. And remember that you will add those in same fashion. But in the case of alkynes, we can have 3 different outcomes. If we use hydrogen, just hydrogen with a metal, you would go straight from the alkyne to the alkene. But if you want to stop that reduction, do a partial reduction to an alkene, there is a couple conditions we need to remember. One is using a poison catalyst, but that is a zinc addition. It will give you the cis alkene. The other condition is dissolving metal. So here, sodium in ammonia will give you the trans alkene. So this was different and similar in the two reactions.